Welcome to Part 4 topic, Ensuring Data Protection Part. 4 introduces the critical role of monitoring, logging, and visibility in cloud security. While strong identity and network controls help prevent many security issues, no environment can be considered secure without the ability to see what is happening inside it. This chapter explains why visibility is essential for detecting misconfigurations, identifying suspicious behavior, and responding to incidents before they escalate. The chapter sets the foundation for understanding how Google Cloud captures activity across users, services, and resources, and how this information can be used to build situational awareness. It highlights that security is not a one-time setup, but an ongoing process that depends on continuous observation, analysis, and response. By the end of the chapter, the reader is guided toward thinking of monitoring and logging not as optional tools, but as core security controls that enable accountability, compliance, and rapid incident response. Topic: protecting sensitive data and preventing data loss. Sensitive data is one of the most valuable assets in any cloud environment. It can include customer information, personal identifiers, financial records, intellectual property, and internal business data. Protecting this data is not only a technical requirement, but also a legal and ethical responsibility. A single leak can damage trust, trigger compliance violations, and cause long-term harm to an organization. In the cloud, data does not sit in just one place. It moves between services, is stored in different formats, and is accessed by users, applications, and automated systems. Because of this constant movement, protecting sensitive data requires more than simple access controls. It requires visibility, classification, and continuous monitoring to ensure data is handled correctly at every stage of its life cycle. The first step in protecting sensitive data is knowing where it exists. Many organizations store vast amounts of data without clearly understanding what is inside it. This is risky. Sensitive information can end up in places it does not belong, such as logs, backups, or shared storage buckets. Identifying and classifying data helps security teams understand what needs the highest level of protection and where controls must be applied most strictly. Once data is identified, access must be tightly controlled. Only users and services that genuinely need access should have it, and only for the specific purpose required. This reduces the chances of accidental exposure and limits the damage if an account is compromised. Access decisions should be intentional, reviewed regularly, and adjusted as roles and workloads change. Encryption plays a central role in data protection. Data should be encrypted while stored and while moving across networks. This ensures that even if data is intercepted or accessed without authorization, it cannot be read or misused. In cloud environments, encryption is often handled automatically, but understanding how keys are managed and who can access them is critical for maintaining trust and compliance. Preventing data loss also means watching how data leaves the environment. Data loss prevention is not just about hackers stealing information. It also includes accidental sharing, misconfigured permissions, and employees unintentionally exposing sensitive content. Monitoring tools help detect unusual access patterns, large data exports, or transfers to unapproved locations. When something abnormal occurs, alerts can trigger investigations before real damage is done. Another important aspect is separating environments and workloads. Sensitive data should not be mixed freely with less critical data. By isolating systems, using separate projects or networks, and restricting data sharing paths, organizations reduce the risk that a single mistake exposes everything at once. This approach directly supports the principle of limiting the blast radius. Protecting sensitive data is not a one-time task. Data constantly changes, new services are added, and access needs evolve. Regular audits, policy reviews, and monitoring ensure that protections remain effective over time. In the cloud, strong data protection is achieved not by a single tool, but by combining visibility, access control, encryption, and continuous oversight into a unified strategy that keeps critical information safe. Topic: understanding data de-identification. Process in any cloud environment. Data is one of the most valuable assets an organization owns. Among that data, some information is especially sensitive. This may include personal details, financial records, health information, or confidential business data. Protecting this kind of information is not only a security requirement, but often a legal and regulatory obligation. This is where the concept of data de-identification becomes essential. Data de-identification is the process of transforming sensitive data so that it can no longer be directly linked to an individual or a specific entity. The goal is not to destroy the data, but to reduce the risk associated with storing, processing, and sharing it. By removing or obscuring identifying elements, organizations can continue to use the data for analytics, testing, or machine learning, while significantly lowering the chance of misuse or exposure. To understand this process, imagine a database that contains customer records. Each record may include names, phone numbers, email addresses, and government-issued identifiers. If this data is accessed by unauthorized users or leaked, the impact can be severe. Data de-identification works by modifying these sensitive fields so that they no longer reveal real identities. The remaining data still holds value for trends, patterns, and insights, but it no longer exposes individuals. One common approach in de-identification is masking. In this method, sensitive values are partially hidden or replaced with placeholder characters. For example, only the last few digits of an identification number may be visible, while the rest is concealed. This allows systems and users to recognize records without seeing the full sensitive value. Another approach is tokenization. Here, sensitive data is replaced with a randomly generated token. The original value is stored securely in a separate system, and only authorized services can map the token back to the real data. If the token is exposed, it is meaningless on its own. This technique is widely used in payment systems and environments that require strong isolation of sensitive information. Generalization is also used in de-identification. Instead of storing exact values, data is converted into broader categories. For example, a precise age may be replaced with an age range, or a full address may be reduced to a city or region. This reduces precision, but preserves usefulness for analysis while lowering privacy risks. In more advanced scenarios, encryption and cryptographic transformations play a role. Data may be encrypted at rest and in transit, and in some cases transformed using deterministic or format-preserving techniques. This ensures that even if data is accessed, it cannot be understood without proper authorization and keys. Within Google Cloud, data de-identification is closely tied to services designed to detect and protect sensitive information. These services can automatically identify sensitive data types and apply transformations consistently across datasets. This reduces human error and ensures that protection is applied at scale, even as data grows and systems become more complex. The most important idea behind data de-identification is risk reduction. No system can guarantee that breaches will never happen, but de-identification ensures that if data is exposed, its impact is limited. Attackers gain access to obscured or meaningless values instead of real identities. The blast radius of a data leak becomes smaller. Ultimately, understanding the data de-identification process shifts the focus from simply locking data away to using it responsibly. It allows organizations to balance security, privacy, and innovation. Sensitive data remains protected, compliance requirements are supported, and the organization can continue to extract value from its data without exposing what matters most. Configuring sensitive data protection, client libraries protecting sensitive data in the cloud, is not only about where data is stored, but also about how it is inspected, classified, and handled as it moves through applications. In modern cloud systems, data often flows continuously between services, databases, APIs, and external systems. Within this flow, sensitive information such as personal identifiers, financial details, or credentials can easily be exposed if it is not carefully managed. Sensitive data protection in Google Cloud provides a way to automatically discover and classify sensitive information. When applications are written in Go, this capability can be integrated directly into the application logic by using sensitive data protection Go client libraries. These libraries allow developers to programmatically inspect data and take action before that data is stored, logged, or transmitted. At its core, the Go client library acts as a secure bridge between your application and the sensitive data protection service. Instead of manually scanning data or relying on after-the-fact audits, the application can actively send content to the service for analysis. The service evaluates the data using built-in detectors that recognize common sensitive data types, such as email addresses, phone numbers, credit card numbers, and government-issued identifiers. Once the data is analyzed, the application receives structured results that describe what sensitive information was found and where it appears. This allows developers to make intelligent decisions in real time. For example, an application might block a request that contains sensitive data, redact certain fields before writing logs, or apply masking before storing information in a database. The key idea is that protection happens automatically and consistently, without relying on human judgment at every step. Using the Go client library also supports the principle of prevention rather than reaction. Instead of discovering a data leak after it has occurred, applications can stop sensitive data from being exposed in the first place. This is especially important for logs, debugging output, and analytics pipelines, where sensitive information can easily be copied and retained unintentionally. From a security perspective, this approach reduces risk across the entire system. Even if a developer accidentally includes sensitive data in an application flow, the detection logic remains in place as a safety net. From a compliance perspective, it helps organizations meet regulatory requirements by demonstrating that sensitive data is actively identified and protected. Configuring and using the Go client library also reinforces separation of responsibilities. Security teams define what types of data are considered sensitive, while developers integrate detection into application workflows. This collaboration ensures that protection is built into the system design, not added later as an afterthought. In practical terms, integrating sensitive data protection through Go client libraries turns data protection into a continuous process. Every piece of data can be evaluated as it moves through the application. This creates a strong foundation for preventing data loss, maintaining trust, and ensuring that sensitive information remains under control, even in complex and fast-moving cloud environments. Topic inspecting and redacting PII from text. Every organization handles sensitive information, whether it is customer names, email addresses, phone numbers, national identification numbers, or financial details. This type of information is known as personally identifiable information, or PII. If exposed, even unintentionally, it can lead to serious consequences such as identity theft, regulatory penalties, and loss of trust. Inspecting and redacting PII from text is a critical step in preventing data loss and protecting privacy in the cloud. In modern cloud environments, sensitive data often appears in places people do not immediately expect. It may show up in application logs, support tickets, chat messages, uploaded documents, or text processed by machine learning systems. Developers may log request payloads for debugging. Support teams may copy user data into internal tools. Over time, these small actions can create large collections of sensitive data scattered across systems that were never designed to store it securely. Inspecting text for PII means automatically scanning content to identify sensitive information before it is misused or exposed. Instead of relying on humans to notice every email address or identification number, the system analyzes text using predefined patterns and classifiers. These classifiers are trained to recognize common types of PII such as names, phone numbers, credit card numbers, government IDs, and health-related information. This inspection can happen in real time as data is ingested, or continuously as stored data is reviewed. Once sensitive data is detected, redaction becomes the next line of defense. Redaction means masking, removing, or replacing sensitive portions of text so that the information is no longer visible or usable. For example, a full credit card number can be replaced with a few visible digits and masked characters, or an email address can be partially hidden. The goal is to preserve the usefulness of the data while eliminating the risk of exposing private details. Redaction is especially important for logs and analytic systems. Logs are widely accessible to engineers, operators, and sometimes third-party tools. If logs contain raw PII, every person or system with log access becomes a potential data exposure point. By inspecting and redacting PII before logs are stored or shared, organizations dramatically reduce their attack surface without sacrificing observability. This process also plays a major role in regulatory compliance. Laws and standards around the world require organizations to protect personal data and limit who can see it. Automatically inspecting and redacting PII helps enforce these requirements consistently, even as systems scale and change. It ensures that sensitive information is handled according to policy, not individual judgment. Beyond security and compliance, inspecting and redacting PII supports safer innovation. Teams can use data for testing, debugging, and analysis without risking real user privacy. Machine learning models can be trained on sanitized text. Support teams can collaborate without sharing full personal details. The organization gains flexibility while maintaining strong privacy boundaries. Ultimately, inspecting and redacting PII from text transforms data protection from a manual, error-prone task into a reliable, automated control. It acknowledges that sensitive data will inevitably flow through systems, and instead of trying to stop that flow entirely, it focuses on making sure the data is detected, protected, and minimized at every step. This approach is a cornerstone of effective data loss prevention and a key element of building trust in cloud-based systems. Inspecting and redacting PII from images in modern cloud environments. Sensitive information is no longer limited to text stored in databases or documents. Personal data often appears inside images. Photographs of identity cards, scanned forms, invoices, medical reports, and handwritten notes can all contain personally identifiable information, commonly known as PII. Protecting this information is critical because once an image is stored or shared without safeguards, sensitive data can easily be exposed, copied, or misused. Inspecting and redacting PII from images is about ensuring that sensitive visual data does not become a hidden security risk. Unlike text files, images cannot be protected simply by keyword searches or basic access controls. The data is embedded visually, which means security systems must be able to understand what is inside the image itself. This is where intelligent inspection becomes essential. The process begins by analyzing images using machine learning-based vision services that can detect text and recognizable patterns. These systems scan images to identify content such as names, phone numbers, email addresses, government ID numbers, credit card numbers, and other sensitive identifiers. Even when text is handwritten or embedded within complex backgrounds, advanced image analysis can extract and classify it with high accuracy. Once sensitive information is detected, redaction is applied to prevent exposure. Redaction means permanently obscuring specific parts of the image so that the underlying data cannot be recovered. This might involve blurring faces, masking text fields, or replacing sensitive areas with solid blocks. The goal is to ensure that only the minimum necessary information remains visible, while all personal or confidential data is removed. This capability is especially important in automated workflows. Images are often uploaded by users, processed by applications, and stored for long periods of time. Manually reviewing every image is not practical at scale. Automated inspection and redaction ensures that sensitive data is protected the moment it enters the system, before it can be accessed, shared, or logged elsewhere. Preventing data loss through image inspection also supports regulatory compliance. Many data protection laws require organizations to minimize the collection and storage of personal data and to protect it from unauthorized access. By detecting and redacting PII early, organizations reduce the risk of accidental exposure and demonstrate that strong controls are in place to safeguard user information. From a security perspective, this approach limits the blast radius of a potential incident. Even if an image storage system is compromised, the attacker does not gain access to raw personal data because it has already been removed or obscured. This transforms images from high-risk assets into safer, compliance-friendly resources. Inspecting and redacting PII from images reinforces a key idea in cloud security. Sensitive data must be protected wherever it exists, in any format. By treating images with the same level of care as structured data, organizations can close a critical security gap and ensure that privacy protection extends across the entire cloud environment. Configuring tokenization, pseudonymization. When organizations move sensitive data into the cloud, one question quickly becomes unavoidable. How do you continue using that data without exposing what truly matters? This is where tokenization, also known as pseudonymization, plays a critical role in protecting sensitive information and preventing data loss. Tokenization works by replacing sensitive data with a non-sensitive substitute called a token. The token looks like real data and can be stored, processed, and shared safely, but it has no meaningful value on its own. The original sensitive data is stored separately in a secure system, often referred to as a token vault. Without access to this vault, the token is useless to an attacker. To understand this clearly, imagine a database that stores customer credit card numbers. Instead of saving the real card numbers, the system replaces each one with a random-looking token. Applications use the token for everyday operations, such as tracking transactions or linking records. The real card number is never exposed during normal processing. Only authorized systems, under strict controls, can convert the token back to the original value when absolutely necessary. Configuring tokenization in a cloud environment begins with identifying which data elements are truly sensitive. This may include financial details, personal identifiers, health records, or authentication secrets. Once identified, these fields are marked for tokenization before they are written to storage, logs, analytics systems, or shared with downstream services. The next step involves defining how tokens are generated. Tokens must not be mathematically reversible and should not reveal patterns from the original data. This ensures that even if tokens are leaked, they cannot be reverse-engineered to reconstruct the sensitive values. Strong randomness and proper key management are essential to maintain this separation. Access control is central to a secure tokenization setup. Only a minimal number of trusted services or users should be allowed to detokenize data. This access is typically protected using strict identity and access management policies, auditing, and logging. Every request to retrieve original data can be monitored, recorded, and reviewed, creating a clear accountability trail. Tokenization also significantly reduces the blast radius of a data breach. If a database, backup, or analytics system is compromised, attackers gain access only to tokens, not real data. This dramatically lowers the impact of incidents and can simplify regulatory compliance, as many regulations treat tokenized data as less sensitive when properly implemented. Another important advantage is operational flexibility. Tokenized data can safely move through development, testing, analytics, and reporting systems without exposing real customer information. Teams can work with realistic data formats while maintaining strong privacy protections. In practice, tokenization becomes a powerful layer in a broader data protection strategy. It does not replace encryption, access controls, or monitoring, but works alongside them. By separating data usability from data sensitivity, tokenization allows organizations to unlock the value of their data while keeping the most critical information protected, controlled, and resilient against loss or misuse. Configuring format-preserving encryption, FPE in modern cloud environments. Protecting sensitive data is not just about locking it away. Data often needs to be processed, analyzed, searched, or shared with other systems. This creates a challenge. How do you protect sensitive information while still allowing applications to function normally? Format-preserving encryption addresses this exact problem. Format-preserving encryption, commonly called FPE, is a special type of encryption that keeps the original format of the data intact. Unlike traditional encryption, which turns data into an unreadable block of random characters, FPE transforms the data into an encrypted value that looks structurally the same as the original. A credit card number remains a credit card, shaped number. A national ID remains the same length and character pattern. A phone number still looks like a phone number. This matters because many applications and databases are built with strict format expectations. They validate input lengths, character types, and patterns. If traditional encryption were used, those systems would often break or require significant redesign. With FPE, sensitive data can be encrypted without changing database schemas, application logic, or validation rules. The system continues to operate as expected, but the real data is no longer exposed. In Google Cloud, format-preserving encryption is typically implemented using Cloud Key Management Service in combination with specialized cryptographic libraries or services. The encryption keys are centrally managed, protected, and audited. This ensures that even if encrypted data is leaked, it cannot be reversed without access to the keys, which remain securely controlled. One of the most important benefits of FPE is its role in data loss prevention. When sensitive fields such as account numbers, identifiers, or personal details are encrypted at rest, and in transit, accidental exposure becomes far less dangerous. Logs, backups, analytics outputs, and test environments may still contain data, but that data is unusable to unauthorized parties. Even developers and operators who do not need access to the original values only see protected versions. Configuring format-preserving encryption requires careful planning. First, organizations must identify which data elements are truly sensitive and need protection. Encrypting everything may seem safe, but it can introduce unnecessary complexity. FPE is most effective when applied to high-risk fields that are frequently processed, but rarely need to be viewed in plain text. Next comes key management. Encryption is only as strong as the protection around its keys. Keys should be stored in Cloud KMS, rotated regularly, and access should be limited using strict identity and access controls. Only systems that genuinely need to encrypt or decrypt data should be allowed to use the keys. Human access should be minimized or eliminated wherever possible. Another critical aspect is access separation. Even within an application, not every component needs the ability to decrypt data. Some services may only need encrypted values for storage or comparison, while others may require temporary decryption for business logic. Designing these boundaries carefully helps limit the impact of a compromise and reduces the blast radius if something goes wrong. Format-preserving encryption also supports compliance and regulatory requirements. Many data protection standards require sensitive information to be encrypted, masked, or tokenized. Because FPE protects data while preserving usability, it helps organizations meet compliance goals without sacrificing system functionality or performance. In essence, format-preserving encryption allows security to blend into the background. Applications keep working. Data flows normally. But beneath the surface, sensitive information is protected at all times. By configuring FPE correctly, organizations take a major step toward preventing data loss, reducing risk, and building cloud systems that are secure by design rather than secure by afterthought. Topic: restricting column access to BigQuery datasets in modern data platforms. Not all data carries the same level of sensitivity. Within a single dataset, some columns may contain harmless information such as timestamps or product categories, while other columns may store highly sensitive details like personal identifiers, financial data, or confidential business metrics. Treating all columns equally can expose critical information to users who do not need to see it. This is why restricting column access in BigQuery plays a vital role in protecting sensitive data and preventing data loss. BigQuery allows organizations to control access at a much more granular level than just the dataset or table. Instead of granting users permission to view an entire table, access can be limited to specific columns. This ensures that users can perform their jobs effectively without being exposed to sensitive information that falls outside their responsibilities. To understand why this matters, imagine a dataset containing customer information. Analysts may need access to purchase history and usage patterns to generate reports, but they may not need to see names, phone numbers, or identification details. If full table access is granted, sensitive data becomes visible by default, increasing the risk of accidental exposure, misuse, or compliance violations. By restricting access to only the required columns, the organization significantly reduces this risk. Column-level access control in BigQuery is enforced through identity and access management policies. Permissions are defined in a way that allows users or groups to query only specific columns, while the rest of the data remains hidden. When a user runs a query, BigQuery automatically checks these permissions and returns only the columns they are authorized to see. Restricted columns are effectively invisible, even though they still exist in the table. This approach supports the principle of least privilege in a very practical way. Instead of broad access that must be carefully monitored, permissions are designed to match real business needs from the start. Users get exactly what they need, and nothing more. This not only improves security, but also simplifies audits and access reviews, because permissions are clearly scoped and easier to justify. Restricting column access also helps prevent unintentional data leaks. Many data loss incidents are not caused by attackers, but by internal users who accidentally export, share, or misuse data they had no reason to access. When sensitive columns are never exposed to those users, the risk of such mistakes is dramatically reduced. From a compliance perspective, column-level security is especially important. Regulations often require strict controls over personal and confidential data, including who can access it and how it is used. By limiting access at the column level, organizations can demonstrate that sensitive information is protected by design, not just by policy. This makes it easier to meet regulatory requirements and respond confidently to audits. In practice, restricting column access in BigQuery allows organizations to safely share data across teams while maintaining strong security boundaries. Data remains centralized and usable, but sensitive information stays protected. This balance between accessibility and protection is a key part of preventing data loss and building trust in cloud-based analytics systems. Securing secrets with Secret Manager in every cloud environment. There are certain pieces of information that must be protected at all costs. These include passwords, API keys, database credentials, encryption keys, and tokens used by applications to authenticate with other services. Collectively, these are known as secrets. If a secret is exposed, even accidentally, it can give attackers direct access to systems without triggering traditional security alarms. Securing secrets is therefore a critical part of preventing data loss. One common mistake in cloud environments is storing secrets directly inside application code, configuration files, or environment variables that are loosely controlled. These secrets can end up in source code repositories, logs, backups, or shared files. Once exposed, they are difficult to track and even harder to fully revoke. Secret Manager is designed to eliminate this risk by providing a centralized, secure place to store and manage secrets. Secret Manager allows organizations to store sensitive values securely, separate from application code. Instead of hard-coding a password or API key, applications retrieve the secret dynamically at runtime. This means the secret never needs to live inside the application itself. If the secret changes, the application does not need to be rewritten or redeployed. Only the stored secret is updated, and access continues seamlessly. Access to secrets is tightly controlled using identity and access management. Only specific identities, such as service accounts or approved users, are allowed to view or use a secret. Permissions can be scoped so that an application can access only the exact secret it needs and nothing more. This follows the principle of least privilege and significantly reduces the impact if an identity is compromised. Secret Manager also supports versioning, which adds an important layer of safety and control. When a secret needs to be rotated, a new version can be created while older versions are kept temporarily for rollback or auditing. This makes secret rotation a controlled and predictable process rather than a risky manual change. Regular rotation reduces the window of opportunity for attackers if a secret is leaked. Another critical benefit is auditing and visibility. Every access to a secret can be logged, allowing security teams to see when secrets are accessed, by whom, and from where. Unusual access patterns can indicate misconfigurations or potential breaches. This visibility turns secrets from hidden vulnerabilities into monitored security assets. Secret Manager also integrates naturally with other Google Cloud services. Workloads running on virtual machines, containers, or serverless platforms can authenticate using their service identity and securely retrieve secrets without managing credentials themselves. This removes the need for shared passwords and reduces operational complexity. By using Secret Manager, organizations shift from treating secrets as static values to treating them as protected resources. Secrets are centrally managed, access is controlled, usage is monitored, and rotation is simplified. This approach dramatically reduces the risk of accidental exposure and plays a key role in protecting sensitive data and preventing data loss in modern cloud environments. Managing encryption at rest, in transit, and in use data is one of the most valuable assets in any cloud environment. It includes customer information, business records, application secrets, and intellectual property. Protecting this data is a core responsibility of cloud security, and encryption is one of the most powerful tools used to achieve that protection. In this section, we explore how encryption works in Google Cloud when data is stored, when it moves across networks, and even while it is actively being used. Encryption at rest focuses on protecting data that is stored on disks, databases, backups, and storage services. When data sits idle, it is still vulnerable to threats such as unauthorized access, hardware theft, or improper disposal. Google Cloud automatically encrypts data at rest by default using strong cryptographic algorithms. This means that even if someone were to gain physical access to the storage media, the data would be unreadable without the proper encryption keys. For most services, this encryption happens transparently, without requiring any action from the user. Behind the scenes, encryption at rest relies on encryption keys. Google Cloud manages these keys securely using a layered key management system. Each piece of data is encrypted with a data encryption key, which is itself protected by higher-level keys. This design limits exposure and ensures that no single key can unlock everything. For organizations that need more control, Google Cloud allows customers to manage their own encryption keys. This gives security teams the ability to control key rotation, disable keys if needed, and meet strict compliance or regulatory requirements. Encryption in transit protects data as it moves from one place to another. This includes traffic between users and applications, between services within the cloud, and between on-premises systems and Google Cloud. Without encryption, data traveling across networks could be intercepted or modified by attackers. To prevent this, Google Cloud uses secure communication protocols that encrypt data before it is transmitted and decrypt it only at the intended destination. Most communication within Google Cloud is encrypted automatically while in transit, even when traffic stays within Google's internal network. When data crosses public networks, secure protocols ensure confidentiality and integrity. This means that attackers cannot easily read or tamper with the data, even if they manage to observe the traffic. For applications, this creates a secure foundation where sensitive information such as credentials, tokens, and personal data are protected during every interaction. Encryption in use represents a more advanced layer of data protection. Traditionally, data must be decrypted before it can be processed, which creates a brief window where sensitive information exists in plain form in memory. Encryption in use aims to reduce this risk by protecting data even while it is being processed. Google Cloud supports technologies that allow computations to occur in isolated and protected environments, such as secure enclaves. These environments help ensure that even system administrators or compromised components cannot easily access sensitive data during processing. Managing encryption effectively requires more than just turning it on. It involves understanding where data lives, how it moves, and who has access to the keys that protect it. Key management becomes a critical part of the security strategy. Organizations must decide whether to rely on Google-managed keys or customer-managed keys, how often keys should be rotated, and how access to keys is controlled and audited. When encryption is applied consistently across data at rest, in transit, and in use, it creates multiple layers of protection. Even if one control fails, the data remains protected by another. This layered approach significantly reduces the risk of data loss, unauthorized disclosure, and large-scale breaches. In the end, encryption is not just a technical feature. It is a foundational trust mechanism that ensures sensitive data remains protected throughout its entire lifecycle in the cloud. Summary of Part 4. Here is a clear, exam-focused summary of Part 4 from the Google Cloud Professional Cloud Security Engineer Certification Companion, based directly on the chapter contents. And Flow Part 4 focuses on protecting data, the most valuable asset in any cloud environment. It explains how Google Cloud helps security engineers discover, classify, protect, encrypt, and control access to sensitive data throughout its entire lifecycle. The chapter begins with protecting sensitive data and preventing data loss using sensitive data protection, formerly Cloud DLP. It shows how organizations can automatically identify, inspect, classify, redact, tokenize, or mask sensitive information such as PII in text, images, and structured data. These techniques reduce the risk of accidental exposure while still allowing data to be processed or shared safely. Next, the chapter explores data de-identification techniques, including redaction, tokenization, and format-preserving encryption, FPE. These methods help organizations use realistic-looking data without exposing real values, which is especially important for analytics, testing, and compliance-driven workloads. A major portion of the chapter is dedicated to encryption. It explains how Google Cloud protects data at rest, in transit, and in use, emphasizing the confidentiality, integrity, and availability CIA triad. The chapter covers Cloud Key Management Service, Cloud KMS, and different key models such as Google Managed Keys, Customer Managed Encryption Keys, CMEK, Customer Supplied Encryption Keys, CSEK, and External Key Manager, EKM. It also explains when to use symmetric versus asymmetric encryption, key rotation, and access control using IAM. The chapter then addresses encryption in transit, highlighting that Google Cloud encrypts traffic by default within and across its infrastructure, while also supporting additional protections such as ISEC, TLS, and managed certificates for external communication. To protect data while it is being processed, the chapter introduces confidential computing. These technologies reduce the attack surface by isolating workloads and protecting data in memory, even from privileged system access, using services like confidential VMs and confidential GKE nodes. The chapter also covers securing secrets using Secret Manager, explaining best practices for storing, accessing, rotating, and auditing sensitive credentials without hard-coding them into applications or exposing them through environment variables. Finally, Part 4 looks ahead to modern workloads by addressing security and privacy in AI and ML systems. It highlights the importance of protecting training data, models, and inference pipelines from unintentional data leakage, misuse, or exploitation. Overall, Part 4 teaches how to design a layered, defense-in-depth data protection strategy in Google Cloud, combining discovery, encryption, access control, isolation, and monitoring to ensure sensitive data remains secure, compliant, and trustworthy across all stages of its life cycle.